So let's continue the chapter 3 of fine-tuning a pre-trained model. We have already talked that this step of fine-tuning a pre-trained model is where we add the most improvement to existing model. So most of the problem statements you might have, the goal of accuracy you will have will most likely be met by fine-tuning. It's a very fundamental thing. And now in this video, we will see how to fine tune with Hugging Face Trainer API. So Hugging Face has given us a lot of amazing libraries. It has given us Hugging Face datasets, which allows us, datasets is a library by Hugging Face. So which allows us to download any datasets in just a standard way. Similarly, it has also given us a transformer library, which allows us to use all transformer models in a centralized way. Okay. So for fine tuning a model, we first start with get a data set, get the model, and then kind of like we move up forward from there. So just get the whole thing started. So fine tuning a model. Before we get to that, let's just set up a standard pipeline, and that this code you should be familiar with. So get a data set, download the data set by using Hugging Face datasets load dataset function. So if I import dataset library as is, then I can say datasets dot load dataset. Or people import this over library separately, but I don't like it because you then need to remember this library. You don't know where it is coming from, but it makes sense. You have dataset from where you get load dataset. And these are the data sets which are important for NLP. So glue is a really important data set. We have already talked about this in last lecture, that this has a few tasks which allow us to understand any language. The tasks are a single a sentence ke task hai. Some of the tasks are whether it is toxic or not, and some of them whether it is positive or negative. And then two other tasks are sentence similarity. Is something a paraphrase or not? Is it saying the same information or not? And something which talks about natural language logic, whether two sentences are related to each other, contradictory to each other, things like that. So NLI is a data set which comes under this. So three kinds of tasks, one all present in this glue data set, and here we are choosing a data set MRPC, which is, let's check, MRPC is here. So sentence similarity and we are using a much smaller data set. Why? Because it's much easier on RAM, but we could do this on QQP easily. This has 300,000 data points. So you download data set, you have a checkpoint, and from that you download a tokenizer also. All same format, Hugging Face underscore transformers dot auto tokenizer dot from pre-trade. Always, always, always. And then you specify checkpoint. So step number one, data set. Step number two, tokenizer. Step number three, tokenized data set, and done. Okay. So let me execute this. Connect without TPU. So I think it's gonna take time. Oh, perfect. Awesome. Okay. So then standard pipeline, you have data set, you have tokenizer, and after tokenizer, you have third, which is the final part, which is our model. Model. So this is, let's make it tokenized data set. Okay. So here in model, again, same way, Hugging Face underscore transformers. Just how we did for tokenizer. Let me copy paste the same sentence here so that you can also see. So you see, they are exactly the same things. They're exactly the same way. So it's very easy to remember. It's because it is standardized. So you download a model, and here I have said auto model for a specific task. This is important because Hugging Face has something called as task specific head. In last video, I used the analogy of, if you have played God of War, we have head of Mimir. If you have read Harry Potter, we have head of Sir Nicholas Flamel, or any, severed head analogy you want to take. Different heads have different intelligence. Or you have Altered Carbon TV series in which different intelligence is saved in the stacks of disk. Or you have Matrix where I think, they, simply upload the knowledge. But anyways, intelligence is part of a head. Different heads have different intelligence. So sequence classification has a different head. Sentence sentiment classification has a different head. Inference tasks, each of the tasks of a different type has a different head. So this is how Hugging Face kind of like deals with intelligence. So we download a model automatically for a specific tasks. This is the head. Okay. And when you execute this, I have given this option of checkpoint. I'm specifying that I want to use this for two labels I'm choosing. And I'm saying force download equal to true. What this force download does is it allows us to understand and see that model, which is a pre-trained model, is, values in memory, RAM. It is 436 MBs worth of floating point values. That is what is a pre-trained model. A pre-trained model. This is what we have here. Okay, pre-trained model. If you want to check into more detail, you should check this video, Epic History of Large Language Models by Campus X. It's an excellent, 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 excellent research which goes over the entire overview of the field, starting from 2015, 16, or 13, and how it has evolved in four main stages. So in less than 1.5 hours, you understand these all four stages. And when you understand the overview first, then you can check the internal details a lot better. So for this detailed thing, before you go into reading the essential research papers, because everything is based on just these three things: attention, GPT, and BERT. Everything in NLP is based on attention is all you need, GPT, and BERT. Three different research papers. So before diving into details, check the overview first. Okay. Now, after executing this, please pay attention to this, something which is coming here. It says some weights of BERT sequence classification were not initialized from model checkpoint. They are newly initialized. A very interesting phrase. It is saying it has classifier.bias and classifier.weight. They are completely newly initialized. They don't have any old knowledge. You know what they are? You know what I was talking about? Head. Right now, sequence classification is a head which does the classification. It is called as a classifier here, and only that final classifier doesn't have existing knowledge. But this auto model does. So 435 megabytes worth of tensors that is used. It's the next part which is uninitialized. It's the next part which is unlearned, and we learn that via fine tuning. That's what this fine tuning process is all about. So here, I've said epic history of large language models and research papers, but this thing might take a lot of time. This concept is a bit more complex. You probably might spend a month on understanding these things thoroughly. At least it took me. It still I haven't finished. Attention is all you need paper thoroughly. So it's gonna take time. So till then, you should know hands on, because this thing, if you know theoretically you're not going to do anything, but if you know it practically, you can actually play, build a solution, and into that build understanding later. So research paper, even if you can't understand thoroughly now, you can at least solve a problem. So for that purpose, there are a few methods I recommend which will allow you to be familiar with this model architecture. These methods are: there is a function called as vars in Python. Then you can directly print the model. or we have a state dict function on PyTorch model, or you have torch info summary function. These are the four ways. Do this, you will understand, look at the architecture, try to kind of like print this out, see what does it have, what in features, out features, and try to reverse engineer things, play around with each of these layers individually. You will know a lot of these things, okay, intuitively, because you have directly playing with the end solution, ready-made variable, right? So first printing model, then you will see it has a lot of complicated things. It's a very detailed format. You might find it difficult to understand. So let me simplify it. Model as a variable has three main parts, rather two main parts. First main part is the BERT model. We are using BERT model here. So first main part is BERT is a model pre-trained by Google, which it uses. Output of this goes to then the second part, which is drop out. Now this is doesn't do it's a thing to improve model accuracy. It doesn't add any new information. It kind of like condenses the information further. So BERT is the part number one. This you can kind of like make it two, or you can put it as a hidden step, doesn't matter. And the final part is the actual classification head. So this is how the transformer library looks at it. So classifier head for doing sentence similarity. It is a task specific head. This is pre-trained. This is not trained. We will train it for the specific data set now. Okay. So by checking these methods, you can actually understand, oh, model is made up of these main parts. Okay. So here, if you can check now, BERT is the first part. Then you have dropout as second part, classifier as third part. And as you can see, this BERT is what is the most complex. All of these things, they're all part of BERT. So it becomes a lot easy to understand. Only these three main parts. Okay, fine. I want the last layer's output. It's the output of model.classifier. I want the output of the BERT. We have model.BERT. Output is what we'll have. And inside BERT, if you check, it is also made up of three main parts. BERT has embeddings, encoder, and then pooler. If you check, BERT has embedding first, then encoder, sorry, this encoder, and then it has pooler. And inside encoder, it further has these different things. So you see, it's incremental. It's incremental. So we have model dot bird dot encoder, and inside that encoder you have whatever stuff does it has. So it is complex. Okay, this is how it keeps going. But you should check it as this. You understand these things at fundamental level from here. Okay, so do that. And then if the functions which I talked about was state dict, so if I do model dot state dict, it will give me all the parameters of the model. Here I'm checking just doing model dot classifier state dict. This will show me only untrained, the newly initialized for a specific head we are building. If I want the entire, bird state dict, I will say model.bird.state dict. This will give me all the pre-trained values which Google has trained. They are what, I use. I don't have to learn them because I am using a pre-trained model. So you see, all of those values are here. So I don't need this. What I need is, I just need classifiers. Classifier state dict. Okay, this one. The third way was, Torch Info Summary. It's a very important library. It has few structures which are essential. So every single argument I have chosen here is important. It makes a difference on how this looks, and you should get into habit of using it into format like this. I've chosen number of parameters and parameters percentage. So I can see each layer, how many parameters it has, and what is the percentage of parameters that layer contributes. and if it is trainable or not. So it's very important. I've also chosen var names here. It allows me to print this. Remember model dot classifier? This dot classifier is a variable inside the model. It prints them here. You see, dropout classifier bird. One, two, three. Inside this one, we have one, two, three, four, five, six. Inside encoder, we have layer, and inside that we have many sub layers. The reason they're not being printed is I have chosen depth equal to 3. Instead of depth 3, if I say depth 4, I will be able to see all the layers here. So using depth parameter, you can adjust how are you looking at the model. So it's much easier to see the model this way than simply output like this. You can't understand anything, but understand the model as a variable. Play around with it in Python notebook. Play with it so much that you should be able to, understand the structure of the model thoroughly. Hands-on experience, okay? And these few essential libraries, when you thoroughly kind of like know them, you can easily visualize and understand model a lot better. Okay. So this is, if you say set depth as 5, you can see all the details in one place, but it's not really that uh kind of like, if you only it's only important when you're going into too much detail of it. Okay. Then you have model.config. Transformers library of this thing comes with a configuration setting in which all the essential configuration will be listed in one place. So when you go and read and understand attention research mechanism, a lot of these parameters will make sense. So for now, you can, skip it. But currently, these different ways using model.named parameters, this is a PyTorch function. If I do it like this, it kind of like shows me layer by layer, all layers one by one, and what variables, parameters in vector does it have. So yeah, different ways of, knowing the network. If you can debug, you can, play around with all of these layers. But this is how you build an end-to-end pipeline. So I've talked about this pipeline so that now we can then fine tune a specific model using any data set. Okay. So by taking this ready-made model, let's fine tune it. Okay. So for fine tuning, uh, Hugging Face has done really amazing thing. If you actually notice, okay, if you notice when we downloaded data set, the data set, even if it is petabytes worth long, we can still download the data set while running the code. Because Hugging Face has internally done something really interesting. It has built stuff like this. It has developed some internal kind of a representation which allows you to download the data set irrespective of how big it is. Okay. So when you do that, you don't actually need a PyTorch data loader functionality. So what happens is this leads, because of this, we only need to use Hugging Face datasets and Hugging Face transformers. Just these two libraries and our job can be done. So that's what we are going to do here. We are now going to train the model for a specific task of tell me if these two sentences are similar or not. That's what we did. We downloaded a data set from Glue of sentence similarity, which was smallest because this will have the least load on our memory, RAM of our computer. So sentence similarity, that's what we are going to do. So for that, you need to specify training arguments. Hugging Face asks you specify training arguments as a class. It has a few important things you can adjust. If you check its documentation thing, you will find there are a lot of things you can adjust. but generally people specify output directory where the model will be saved. Evaluation strategy, how frequently the model will be checked, at every step of the way, or do you want to, go through the entire data set and only then check? Or learning rate, how fast you're learning, or how details of training. Do you want to see every step of the way what is happening, or you are going to run it for a day and then check? Stuff like this. So we just specify output directory, which is the standard one. It's good to specify that we know that output directory is test trainer. This is the output directory in which the details will be saved. Okay. So trainer we specify like this: Hugging Face transformers dot trainer, and it is initialized with the model, training arguments, and the data set we have downloaded. Also tokenizer and also data collator. So if you specify it in format, anyway, it's very easy, right? Everything you created, there are just few things you need to do. Once you kind of like build them, all you need to do is go into the trainer API, kind of like specify it like this, and just evaluate. Okay, so just get the prediction. So what model generally does is, whenever you get the output, right, it doesn't tell us if it is positive or negative. It kind of like answers in number. If it is very sure, it will say 1. If it is very sure it is wrong, it will say 0. If it is unsure whether it is 0 or not, the value will be maybe 0.001 or 0.1. So based on value, we are gonna understand how confident it is in its prediction, something like that. So for that, we have something called as logits versus probability. So this is a concept which, more when you go into a bit more detail of this library and model internals, you will understand. So for now, you can just see, what these are: logits are values, and then you convert them into probability, and then you understand which class does it belongs to using argument max or something, and then you simply check how accurate you are. So for sentence similarity, by using ready-made BERT, we achieved 31% accuracy. Not that great, but in by using ready-made, we have actually gotten good enough. So if we can train it on the specific model, we actually get quite good accuracy. So for that, Hugging Face has this function of compute matrix. Check the format like how I have given in the notebook. This is how it is. And the main thing is remains the same. You build a training arguments, then you build a model, and then you build a trainer with these parameters as its argument. I have specified compute matrix as a function to the trainer, and then I simply say trainer dot train, and the training happens. So here is where fine tune of the model for this data set is going to happen, and we are going to get a model with a lot higher accuracy. What has happened now? We have fine-tuned the model. We have fine-tuned the model for doing this sentence classification here. So this evaluation and everything, this fine-tuning of model Hugging Face course, it kind of like talks about this. So this, because in my Google Colab notebook, I didn't get a GPU to run. So it is running very slowly. So let me go here and show you directly that we have reached the end. So you do this, you will get a very good accuracy simply by leveraging existing pre-trained model. This is the fine tuning with trainer API. So as you see, to the trainer API, we only give model arguments of how the training is going to go and dataset. These dataset come from Hugging Face datasets. And the padding thing which we do, we can either do padding inside dataset only, or we use data collator. And data collator is recommended because it helps. Let's just say do it like this. This is the best case recommendation. Tokenizer, reads the data and converts it into tokenizer, right? So all of the trainer takes care of reading the data, then passing it through the model, then learning from the error, calculating the error. So everything happens internally here. Okay, so this is how we fine tune. Any problem you might have, go to Hugging Face. If you say, I want to solve a document question answering problem and I'm going to fine tune my model to be able to answer, let's say, Harry Potter questions. Okay, so I will take a existing model, fine tune it on Harry Potter and some Harry Potter specific questions which I will prepare. And suddenly, my model, which is a general Q&A model, will be a lot accurate on Harry Potter. Why? Because I gave Harry Potter specific data set to it. Even if data set is small, it is going to make a huge impact on the quality. Why? Because I'm using existing Q&A models here. And on that, I'm fine tuning for Harry Potter specific data set, which I will build. That is why fine tuning is so important. When you run the model on a GPU, it will run a lot faster. This is running very slowly because it is running on a CPU. Every second, it is taking 10 seconds to complete one batch learning. This is what this is, 0.1 iteration per second. So it's incredibly slow. On GPU, it will be a lot faster. So fine tune, this is how we fine tune and this is why we fine tune. And then in next lecture, we will actually see the same thing, but everything will also do manually. So if you want to see what is happening at step number 6, step number 20, all of that internal control, the next lecture will actually give you. So this is it for fine tuning section.